In this video, we're going to talk about friction, and friction is really important for many things that we do. We wouldn't be able to walk or drive or really move in any way without friction. So friction is really important to us. We'll talk about three different types of friction. We've got static, kinetic, and rolling friction. All of these friction types are due to an interaction between an object and a surface. And in particular, that interaction is going to be, that force is going to be parallel to the surface. So if I think about any object, right, if I have just an object on an incline and I'll just indicate that there is some friction there on that incline, if I have that object, so it has an interaction with the surface, right? And I can just represent that surface, the force that's due to that interaction between the object and the surface. I can represent that with just some F surface vector, right? But we tend to always analyze our systems. We're going to be thinking about that surface force in terms of the parallel and perpendicular components. So we won't ever write the surface force this way. We will always think about that surface force in terms of the component that is perpendicular to the surface, and that's the force that we call that normal force. And then there's also going to be that component that is parallel to the surface, right? So, but the normal force and the friction, I want you always thinking about that they're kind of just components of that interaction between your object and the surface. So no matter what type of friction we're talking about, we are talking about a component that is parallel to the surface. So if we're dealing with static friction is going to be the force that prevents slipping. So we're going to say prevents slipping. So we're going to call that the static friction. And we're going to give it a notation. So friction is always a lowercase f. And we're going to call static friction is going to be F sub S. So that's our static friction. Kinetic friction is when we do have an object moving, but it is going to be a force that opposes motion. So I'm going to say force that opposes motion. So we have motion, but our object is sliding across the surface. And so as it's sliding across the surface, there's going to be a friction force that's pointing in that direction opposite of the motion. And so we're going to designate this one still lowercase f because it's friction, but we're going to say F sub K. So that's our friction force. We're also going to have rolling friction. So rolling friction is separate from kinetic. So if you think about anything with wheels, so the wheels are spinning and rolling on the surface, and that's different from sliding on the surface. So you can have wheels that would slide on the surface. So for example, if you slam on your brakes or something, kind of lock up the wheels and then skid. So that would be kinetic friction because the wheels would be sliding. But if the wheels are spinning and turning on that surface, we're going to have what's called rolling friction. And so rolling friction is just when we have a wheel rolling on a surface. And so again, we're going to use our lowercase f, and we're just going to use a little L. And I'll talk about each of these in a little bit more detail in the next video, but just to introduce the three types: static, kinetic, and rolling friction. So if we want to think about kind of our model for friction, if we think about static and kinetic specifically, that's what we're going to use primarily in the course. I have three different pictures here. And each of these are just showing a person trying to push on a box. So if you can imagine you're trying to push something really heavy, so maybe it's like a big refrigerator or something, right? So pushing something heavy, we are going to specify that the object, I'm just going to say it's a box, but imagine it's a really heavy box that we're trying to push here. So if the thing that we're trying to push is really heavy, so you can imagine that I might push on that a little bit and get no motion, right? So if we think about what a diagram might look like here, I might say I have some F push that's going this way. This is the person pushing on the box. But if the box isn't moving, there must be some force opposing that motion. And so this is going to be what we call static friction, right? So if that box is not moving, it's static, not kinetic friction. So maybe we try to push on the box a little bit and it doesn't move. And so then we're going to push a little bit harder and it still doesn't move. And so hopefully you have this experience where you can push with different efforts, if you will, and still not get something to move, right? But if I'm going to draw my free body diagram here, so if I make my free body diagram, I need to show that this is a bigger push. So that magnitude is going to be much more. If the box is still not moving, then there must be a bigger opposing force back, right? So that static friction force is still static because we're not moving. So it has to be matching that pushing force. And so that's going to be important for us. The static friction is not going to be a constant force. It's going to be something that is matching the applied force, if you will. The thing that is trying to get us moving, the static friction force is going to be opposing that force and matching its magnitude. If we have the third case, so say I keep pushing a little more, and then again, hopefully you have this experience of pushing on something, and then finally it starts moving. And when it finally starts moving, a lot of times it's going to feel like it's easier to keep pushing, right? So now we did a bigger push, now we're moving. So I still can do my free body diagram. So I still have some applied force here that I'm calling push not applied. So F push. And so now though, we still have a force that's opposing that motion or friction, but now this is a kinetic friction, right? And so that kinetic friction is going to oppose the direction of motion. So here I can even specify, right? We have some V that's moving in that direction to the right. So if we express this, I think it's sometimes helpful to think about this in an XY type of graph here. So here on the horizontal axis, we have the push or the pulling force. So this is like some F. I'm going to make this very generic. So some F applied, right? I'm applying a force to an object in some direction. And then over here on the vertical axis, this is our friction. Okay. And so if we think about what was going on up here in these first two spots, as I increased my applied force, right? So as I go across this way, as I increase the applied force, my friction force also was increasing. So I'm going to have something that looks kind of like this, right? As I get to a certain point, as I keep increasing my applied force, that friction force is going to match that. And it's going to keep going up to some point. Then we said, well, then I get to a certain level of pushing, then it's going to feel a little bit easier. And so we're going to say that this kind of slips. And then it's a little easier to keep the pushing. And so then we're going to get something. And if you actually measure this out, it's pretty close to constant, but it might have some little squigglies in there. So this general relationship though, so this is important to kind of recognize. We're going to define some points here. So I'm going to say that this point here, this point where right before the object starts to move, right before that object starts to slide, we are going to call this my FS max. So this is my static friction, the max value of that static friction. So all the way from here to here, our object is not moving, right? So this is not moving with an A-M, if I can spell moving right. So this is not moving. And then from here on out, so this is motion, right? The object is moving from here to here. So in that region where it's not moving, that's where we have our static friction. And so along this section here, our static friction, if I can write this in here, our static friction is equal to our applied force, right? So it's matching that applied force. If I push harder, the static friction force is pushing back the other way harder, preventing that motion until we get to some max point. Then we're going to get that slippage. And then here, this section all in here, this is where we've got our kinetic friction. So this, if I map this over to our vertical axis there. So this is going to be our F sub K, right? So that kinetic friction is lower than our max static friction, and it's essentially constant, right? So once we start moving, we're going to assume that our kinetic friction is constant. An important point to recognize here is that static friction is not constant, right? That static friction is less than this FS max all the way up until this point. At this point, that's that maximum static friction point. That's where you've pushed as hard as you're pushing, that the static friction can push back in the other direction. And then we're going to get that slippage and shift over into the kinetic. So in the next video, I'm going to talk a little bit more explicitly about the static friction and kinetic friction, introduce the equations that we're going to use, but I'm going to reference back to this graph and this idea that that static friction is not constant, and then up to that max point is actually equal to our applied force.